All right, so let's move on to a new topic. We've been talking about stresses. Now we're going to talk about strain. Now I don't know what you think about strain. If you've already have some ideas of what strain, what that means to you. I kind of think of like if I'm strained, I think it's kind of stretching. Something is stretching me, or I'm stretching something, and that's sort of one type of strain. But it's really kind of a deformation, a change in shape. All right, so when forces are applied to a body, that body can change shape and or size. And so strain right here is a measure of that change, a measure of let's just call it deformation. So it's a measure of the deformation of an object. Strain is a measure of the deformation of an object. Now, two types of thing can cause strain. Two things can cause deformation. Load, right? Forces can cause strain, but also temperature could cause strain. Temperature could cause deformation, right? Something might elongate just due to the temperature, or it might elongate or change shape due to the force. So load-induced strain is deformation caused by load. Or, caused by the forces. And actually, it's really caused by the stress. We'll talk more about that. So, for instance, if you have some object that is shaped like this, if you pull hard enough, right, with this force P, then it might deform it might just be a little bit of deformation, but it might get a little bit longer, right, in those directions, maybe a little bit thinner in the other direction. Okay, right? Can you imagine that? Okay, or now a change in shape, a strain, is not always a stretching or compression. If you have a force up here at the top of this rectangle, let's say, if you have a force right here at the top of this rectangle, then imagine what might happen to it. It might change shape a little bit. This is definitely an exaggeration here, but it might change shape to something like this. We'll talk more about this, but up here, this is a normal strain caused by the normal force, and this is a shear strain caused by a shear force. All right, but temperature-induced strain, for example, what if you have some cantilever beam right here that is fixed right here? So this is deformation due to temperature change. Deformation due to temperature change. Right? Due to delta T. So if you heat this up, might be just a little bit, but might elongate some. So let's say it started at 60 degrees Fahrenheit. Well, at 100 degrees Fahrenheit, it might change shape a little bit. All right. So I mentioned normal and shear strain. We're going to start with normal strain. All right, let's start with normal strain. Normal strain, we're going to label it as this epsilon, Greek letter epsilon. Epsilon is the normal strain. And so this is the measure of elongation. This is the measure of elongation or contraction of a line segment we're going to say a line segment per unit length, right? You can divide it by its total length so that it's normalized, whether you've got a small beam or a very long beam. So let's say its initial length was that dimension right here. Its final length is that dimension right here. Epsilon, the normal strain, is delta L over L. Let's memorize that. Put that in our toolbox for using. Normal strain is delta L over L, right? L final minus L initial over this. In the denominator is going to be L initial. L initial. So let's think about this. Let's think about a few things. Think about the units here. This would be something like meters. This would be something like meters, or maybe millimeters per millimeters. These units cancel out, so it really is unitless. Sometimes, though, you'll see the book or some of these specify the units as, they'll keep it as millimeters per millimeters or inch per inch, and we can do that, but it's unitless. So I would accept it with or without those millimeters per millimeters or inches per inch. Okay, let's think about a few things here. If this is positive, first of all, this denominator is always going to be positive, but if this numerator is positive, that means L final was greater than L initial. That would be elongation. So positive strain is elongation. It's stretched. It got longer. And, of course, a negative strain would be contraction. It got shorter. And that's just like our normal forces. Remember, our normal forces, we said, we'll say that a positive normal force is in tension. And positive tension would cause positive elongation, cause positive strain. Sometimes this epsilon is very small, right? You can imagine that these, especially depending on the material, but it doesn't stretch very much. Fractions of millimeters per, meters and meters long of beams. Maybe like 0.00064 millimeters per millimeter. Sometimes we can specify our strain. As microstrain, right? And so micro is 10 to the negative 6, right? 10 to the negative 6. And so we could, bring this over 6 and say, okay, maybe my normal strain, instead of saying 0.00064, we could say 640 micro strain. All right, so that micro is just a way for us to move this decimal 6 places to get, a number that's not so small. Right. So this is that's a mu, right? Greek letter mu, microstrain. And another thing, sometimes it is defined as a percent. Sometimes it is specified as a percent. Right. Epsilon is 0.003 inches per inch, or 0.3%, right? That percent is like a 100 or 10 to the negative 2. All right, we can move this 2 places and say, oh, well, it's 0.3% is the normal strain.